So our project is on Newton's law of cooling, and Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature, which is the temperature of its surroundings. We can use Newton's law of cooling in a real-world example by seeing how long it takes for an object to either cool down or heat up. In our project, we will be looking at how long it takes for a pie to cool to a specific temperature. We can look at Newton's law of cooling mathematically by using the following differential equation. dt divided by dt equals negative k times T minus T sub a. In this case, the uppercase T stands for temperature, the lowercase t stands for time. We have to solve this differential equation to find a general solution in order to solve Newton's law of cooling problems.
The first step is to algebraically manipulate this equation so that our capital T's are on one side and our lowercase ones are on the other. Divide both sides by capital T and subtract the ambient temperature, or T sub A.
Now we can integrate both sides. The left side of the equation is going to be the natural log of the absolute value of what we have in the denominator. We're using u substitution, where the u would be equal to t minus t sub of a, then du would be 1 dt, thus making this the integral of 1 divided by u times du. So it would be the natural log of the absolute value of u. So this is the natural log of the absolute value of t minus t sub a is equal to negative kt plus c.
Now we can raise both of these to the e power, so we can write this as the absolute value of t minus t sub a is equal to e to the negative kt plus c. This is the same thing as e to the negative kt power times e to the c power. So this should be starting to look familiar because we can rearrange it to be ce to the negative kt power.
So if we are dealing with something hotter than the ambient temperature, the number inside the absolute value will be positive, meaning that we no longer have to worry about the absolute value. We will then add T sub A to both sides. This gets us to the general solution for something that is hotter than the ambient temperature. We could then use this general solution on certain Newton's law of cooling problems.
If we want to look at something that is cooler than ambient temperature, the absolute value will be negative. Thus, after taking the absolute value, the number will turn positive. So this results in T sub A minus T. This is going to be equal to CE to the negative KT. So then, to solve for lowercase t, you add uppercase T to both sides and subtract CE to the negative KT from both sides. You will have T as a function of T is equal to T sub A minus CE to the negative KT.
Just as a review, if we have the differential equation of d capital T meaning temperature over d lowercase t meaning time equal to negative k multiplied by t minus t sub a, we can create a general solution in order to perform Newton's law of cooling problems. Because we have a pie that is a greater temperature than our ambient temperature, we are going to use this general solution equation. Temperature as a function of time is equal to CE to the negative KT plus our ambient temperature, or T sub A.
So for this experiment, our ambient temperature is 20 degrees Celsius. We figured this out by looking at what the room temperature of the house was, which was 68 degrees Fahrenheit. In this experiment, we're going to assume that the temperature does not change. Right out of the 350 degree oven, we took the temperature of our pie, and it was 176 degrees Fahrenheit, or 80 degrees Celsius. We then took the temperature of our pie 2 minutes after we took it out of the oven, and it was 149 degrees Fahrenheit, or 65 degrees Celsius. And after taking this information, we want to know how long it will take for our pie to cool to 23.9 degrees Celsius, or 75 degrees Fahrenheit.
So the first thing that we are going to do is solve for the constant C. The first thing we know is that our ambient temperature is 20 degrees, so we're going to plug that information into our equation, making it CE to the negative KT plus 20. When we use T of 0, it will simplify our CE to the negative KT to 80 equals C plus 20 because E to the 0 is equal to 1. When we subtract 20 from both sides, leaving 60 equal to C. Now we're able to figure out C. Now we know that T of T is equal to 60e to the negative KT plus 20.
Now we are going to solve for K, and we are going to use T of 2 is equal to 65 degrees. So our equation is going to be 65 equals 60e to the negative 2K. For a reminder, we got this 60e from our last equation solving for C. And we have negative 2K because we are solving for K when time was equal to 2. And then plus 20 at the end for our ambient temperature. We then are going to subtract 20 from both sides, and that leaves us with 45 equals 60e to the negative 2k. We then divided both sides by 60 to get e by itself, leaving us with 3/4 equal to e to the negative 2k.
So then to get rid of the e, we're going to take the natural log of both sides. After doing this, we get the natural log of 3/4 equal to negative 2k. So then to solve for k, we're going to multiply by negative 1/2 to get k equals negative 1/2 times the natural log of 3/4. We now have solved for all of our constants.
So we want the pie to cool to 23.9 degrees Celsius, so that is going to be our capital T, or temperature. And we're going to solve for lowercase t, or time. So we'll have 23.9 equals 60e to the 1/2 natural log of 3/4 times t. We then subtracted 20 from both sides, then divided by 60 on both sides. So now we are left with 0.065 equals e to the 1/2 natural log of 3/4 times t. To get rid of the e, we took the natural log of both sides. Then, to finally solve for our t, we took 2, flipping the 1/2 multiplier, times the natural log of 0.065 divided by the natural log of 3/4. After using our calculator to calculate this, we got 19.0002 minutes.
And they said we would never use calculus in our lives.